Hello, everyone. We're going to go ahead and go over section 2.7, which is on combining functions. So we've been looking at functions a lot this section. So we're doing something a little bit more new, a little bit more to do with algebra versus graphing like how we saw in our last section. So we have combining functions. So we're going to go through all the different ways that we combine functions and learn a new way. So as an overview, we can use different ways to combine functions in order to create new functions. So these are things like adding, subtracting, multiplying, and dividing. These are all things that you're going to be familiar with. So we have those four basic ways of combining functions. And then we're going to introduce one new one. The new one being composition. So a new method that we're going to use is composition. This is like using a function as an input for another function instead of like a variable x. So typically what we've seen before when we have a function of f of x, so in those cases we used x as the input. So we got to replace things like numbers with x and whatnot. In this case, we're kind of doing this twice. We're using a variable like x and inputting it into a function, say g. So now we have g of x. And now we're taking all of g of x as an input for a function of f. So we would end up with something like f of g of x. So we're kind of doing this twice over now instead of just the one substitution like with just x. So another kind of example you can have for this is, let's say you have apples. Apples will act as your variable x. And let's say that you want to go ahead, you're going to take your apples, slice them up however you want. And then you're going to go ahead and you're going to put them in the function of dough. So you're going to put some apples in dough. So once you put your apples in dough, it's a new thing. You basically have an unbaked apple pie. So instead, you started with apples. You have an unbaked apple pie, and the last thing it can go into is the oven. So you take your whole unbaked apple pie, you stick it in the oven, and your answer becomes apple pie. So apples just within the dough, something like a function of g of x, is something very different than the end result of a baked apple pie in an oven, considered something like f, like a function f. So we can kind of compare composition functions kind of in that way as well. So we see it's kind of a double, like you're taking something like a variable, you're putting it in a function, and you're taking that result and putting it into another function. So it's kind of this double evaluation almost, because you're evaluating your function at a variable, and then you're evaluating your next function with another function. So that's going to be how that works. But first, let's go ahead and just review our sums, differences, products, and quotients. Very quickly here, these are four basic ways of combining functions. So first off, when we add two functions together, our result is the sum. So like f plus g, that would be the sum. So we're just going to go through the terminology. When we subtract a function from another function, that result is called the difference. So when you hear the difference, you want to subtract. So we have f minus g. When we multiply two functions together, that result is called the product, so something like f times g. And when we divide a function by another function, that result is called the quotient, something like f divided by g. So to sum all of this up in a definition here, we call all of these things algebra of functions. So it's just the different types of operations that we can use to combine functions. So we call this the algebra of functions, the typical types of algebra that we see whenever we have functions. So we're going to let f and g be some functions with domain a and b. So f has domain a, g has domain b. Then our functions f plus g, f minus g, f times g, and f divided by g would be defined as follows. So we have f plus g of x is the same thing as saying f of x plus g of x. And we're going to deal with this domain part. Second here, we're just going to run through the different problems. Same thing if we have f minus g of x, that's the same thing as saying f of x minus g of x. If we have f times g of x, that's equal to f of x times g of x. and f divided by g of x is equal to f of x divided by g of x. So each one of these formats can be simplified into the ones that you see here on the right-hand side, which would make your problem a lot easier to actually work on, knowing that they kind of translate in this way. Now for the domain, we have in the first three here, they're all going to be the same. So we have this domain A, and then we have this upside down U, B. So the upside down U is what's known in statistics as the intersection. So we're saying the domain is A intersect B. And the intersection represents the word both. So in this case, our domain would have to be the values of x that existed in both A and B. So if there were any values of x that were in A that were not in B, they would not be included. Same goes for if there are any values of x that were in domain B that were not in domain A, they would not be included. So your domain is only going to be the values that both domains of the original functions share. So they have to be the same numbers. And that's going to be true for the first three. So we see addition, subtraction, and multiplication. That's all true. Your domain just has to be those values of x that exist in both domains. Then lastly, here we have the domain is x, and we're going to read this out here. This is in set builder notation. We briefly reviewed this a few sections ago. But so our domain says that x is in, that's what this kind of backward E means right here. It means the word in. So x in A intersect B. So any values of x that are in both domains, we would say that g of x just can't be 0. So we're saying for all values of x that are in the domain, the intersection A intersect B, for all values of x, g of x just can't be 0. So we're saying that we found the domain A intersect B. For all values of x that are in there, none of them can actually just allow g of x to be 0 because you can't divide by 0. So the way that this function is set up, we have f of x divided by g of x, so we cannot include any values of x that would make g of x equal 0. So that's what we're saying here in this statement. We'll find our domain the exact same way. The only difference now is that we would just have to also exclude any values of x that make your denominator 0. So, all right, let's go ahead and first we're just going to take a quick look at kind of the difference between unions and intersections really fast in our notes, just so we can get a little bit of a view here of what we're talking about when we say unions and intersections and kind of the difference there. All right, so going on here with the difference between unions and intersections, since we will be using both, or you will at least have seen both at this point, we have seen unions a few times before, and we said that for all intents and purposes, unions stand for the word that we understand to be the word and. So in statistics, they do use different language for unions and intersections. So if you do Google it, it will probably tell you a different word that they represent. But I'm telling you that for our understanding and our level of understanding, we would understand unions to be the word and. It's going to mean everything included in our circles here. So we have Venn diagrams. We have one circle is representing a domain A and the other circle representing domain B. So when we have unions, we're saying everything included in domain A, everything included in domain B, and everything included in both. So a union in Venn diagram would kind of look a little something like this. So it would be everything. It's everything in A, everything in B, and everything in both. So that's kind of the understanding that we have there. When it comes to unions, we mostly use unions in our answers for domain and interval notations. And we kind of do that because it is a little bit different. In our Venn diagram here, we see we have the overlapping circles. So there is a both category, but when it comes to us writing domain and interval notations, we do not have a both category. It would look more like two separate circles domain A and B that we're coloring in, and we're saying, okay, both domains. That's kind of how we include both of them, but there is never that kind of both category. The circles are not overlapping when it comes to interval notation. So that's really why we use unions. It's kind of just a quick and easy symbol to just represent the word like and. Instead of writing the actual word and, we're just saying that it's this thing and it's also this thing, and you know, it's all meshed into one answer at that point. So it's kind of more like a glue that just holds those two answers together to create one whole answer. So that's what we work with when we think about unions. But when it comes to intersections, like how we just saw, we saw domain A intersect B. So when it comes to combining functions, your new function, that f plus g, that new function's domain has to have the values of x that existed in both domains. So in that case, we're looking at this center part, that overlapping of domain A and domain B. So if something exists in A, let's say star. Star exists in domain A, but it is not in B. So it doesn't get included in the new domain because it was not in both domains. And let's say, you know, domain B has heart, and let's say domain A does not have a heart. It is not included in the new domain because it is not in both. But let's say smiley face. You can barely see that. Let's do it. There we go, smiley face. Smiley face is in domain A and it's in domain B. So in that case, it would be included in the domain A intersect B since it is in both domains. So that's the idea there that we're using this with. So that's the difference between unions and intersections. Just a quick little stats preview, I guess. A little stats lesson there. But so since you're going to be seeing them in the future, that's what they mean. So let's go ahead and do our first example. All right, so example 1, using the graph, we're going to calculate the following values. We have this graph here. We have two functions, f, which is in red, and g, which is in blue. And what we're doing here is that using the graphs, we're going to calculate the values. A is f plus g of 0. B is f minus g of 0. C is f times g of 0. And D is f divided by g of 0. So what we're doing here is that we have the 4 different types of ways that we currently know how to combine functions. They're already evaluated at a specific number. In our last slide here, which if we click over here, we said that if we tried to combine functions like saying f plus g of x, that's really just f of x plus g of x. And since our function is already evaluated, we want to evaluate when x is 0. Really what this is asking us is, what is f of 0 plus g of 0? And what's f of 0 minus g of 0? What's f of 0 times g of 0? And what is f of 0 divided by g of 0? So this is really what we're being asked here. And so all we need to do in order to actually find these values is look to our graph. So we're going to verify what our actual values are before we go over to our notes. So we look at our functions here. We have our red function f and blue is g. So we see that they have values for different x values. They have y values for different x values. So if we have our function here and we want to know what is our function value when x is 0, starting with f, we find x equals 0, which is at the origin here on our coordinate plane, and its value for f is 2. That is the y value when x is 0. So our function f of 0 is equal to 2. Then for g, same thing, we're going to find x equals 0 and find the y value, which in our case is -1. So g of 0 is equal to -1. So let's go ahead and really quickly do these calculations in our notes. All right, so here's example 1. We said that f of 0 was 2 and g of 0 was -1. So we're going to use these values. But we're first going to express all our different operations here into its kind of more simplistic version. So we said that f plus g of 0, this was going to be the same thing as f of 0 plus g of 0. So let's go ahead and add these up. F of 0 plus g of 0. F of 0 was 2. G of 0 was -1. And 2 plus -1 is 1. So that's really what we're doing here. So these are going to be pretty simple here. So we're just going to talk our way through it real quick. Part B, it's going to be the same thing. F minus G of 0 is the same thing as saying F of 0 minus G of 0. So we've got 2 minus -1. This is the same thing as saying 2 plus 1 because these will cancel each other out. They can turn into pluses instead. And 2 plus 1 is 3. So this is all we're doing here. F times G of 0 is the same thing as F of 0 times G of 0. So we've got positive 2 times -1, which is equal to -2. And lastly here, f divided by g of 0 is going to be equal to f of 0 divided by g of 0. So this would be 2 divided by -1, which is also -2. So that is those are all of our answers there. So we basically just used that definition that we saw before to replace or rewrite the equations that we were given, just to put it in a little bit of an easier light or fashion here, to make our problems easier for ourselves. So that's how we went ahead and did example 1. So let's go on ahead back to our lecture. All right, so this was example 1 here. Moving on, we can go to example 2. Do a second example now. So example 2 is we're going to let f of x be equal to 1 over x minus 2, and g of x is equal to the square root of x. Then we want to find the following functions and their domains. So part A, we have f plus g. B, we have f minus g. C, we have f times g. And D, we have f divided by g. So we actually have functions now. So we're going to actually find the new functions that come about from adding them together. So we're going to be solving for these new functions and their domains. So now is when we're going to have that A intersect B domains kind of come into play here. So let's go ahead and head on over to our notes to work on this problem. All right, so here we are with example 2. We have our function f and our function g. So we want to go ahead, we're going to add them, subtract them, multiply them, divide them. But before we get started, a really good place to start here would be finding the domain of each function separately. So that'll be that much easier when we have to find the domain of their intersections. So let's go ahead and figure out their domains. Now the easiest way to do this would be to set up number lines for each one and then find its domain that way. So let's go ahead, we're going to set up a number line. Oops, I didn't start off too great there. There we go, number line and a number line. So starting with f of x, we have 1 divided by x minus 2. So the idea here is that we can include any values except anything that would make our denominator equal to 0. So in our case, the only number that would make our denominator equal to 0 would be 2. 2 minus 2 is 0, so we're basically just saying that x cannot be 2. So if we say that 2 is right around here, our domains would include everything except 2. So our domain would be, in this case, our number line starts from -infinity and goes to infinity. So our domain would be -infinity to 2 and 2 to infinity. That's a domain of f of x. So moving on to g of x, we have the square root of x. Now when it comes to square roots, we just can't include any negative numbers. We can include 0, but nothing less than 0. So if we go ahead, we put in 0 right there. We're saying that it can include 0, but nothing less than that. So in our case, whereas before this 2 would have had an open circle around it, which I forgot to put, in this case, we would have a closed circle around 0 because we did include it. And includes everything greater than 0. So in this case, we only have this side of our number line. We don't include the negative side. And this side here, which is going to be our domain, is 0 to infinity. Now, infinity always gets parentheses, and since we included 0, we put a square bracket on it. Forgot to put some arrows on the other one, but it's not a big of a deal anymore. But all right, so those are the two domains of our function. So f of x has the domain negative infinity to 2 and 2 to infinity, whereas g of x only has the domain from 0 to infinity. So let's go ahead. We're going to start off with part A. We're going to find f plus g and find the new domain. So with part A, we have f plus g. Now I wanted to write it like this because you will see occasionally on like homeworks and exams, it can be written a little differently. So in this case, if you see something like f plus g, this insinuates f plus g of x. That's really what we mean here. And let's actually put all those in a different color just so we know it's like a little different here. So it implies f plus g of x, which we know from a few slides ago is the same thing as f of x plus g of x, like that. So this really is insinuating f of x plus g of x. We know what f of x is. We know what g of x is. We can go ahead and we can add them together. So f of x we have is 1 divided by x minus 2. And g of x is the square root of x. Now for this problem here, we have a fraction plus a square root. We don't necessarily have to simplify it any further than that. On a problem like this on your homework, it would accept this answer that we just have right here, the 1 over x minus 2 plus the square root of x. If you did want to simplify it, you could. So this is pretty much a tentative answer right here. If you wanted to simplify it, you could definitely do that. You would just need to make the square root of x have the same denominator, x minus 2, which means that you would have to multiply the square root of x by x minus 2 divided by x minus 2, and then you could combine them. That answer would look like 1 plus the square root of x times x minus 2. All divided by x minus 2. So you can do it. It is doable. It doesn't change anything about the answer, and WebAssign would accept what we have highlighted anyways. So you don't necessarily have to do this. You can if you want to. So that's the idea there. So now that we have added these functions together, we want to find that domain, because remember our domain is A intersect B. And in this case, we're going to say that f has domain A and g has domain B. So for our answer here, and we're going to pick a new color. We're going to go ahead. We're going to, oh, wrong thing that I did there. We're going to go ahead. We're going to pick purple. Let's say purple. We'll add purple to our list here so it's easy to pick. But so our domain is going to be A intersect B. So this is our domain. We know what the domains are for A and B, but we want that combination. So we're going to draw a number line again. So we've got this number line. It goes from negative infinity to infinity. It's a little curvy, but it's okay. It's going to work. And so we're going to do both of our domains. We're going to draw both of what we have above for those number lines. We're going to draw that on one number line. So the important numbers here are 2 and 0. Those are really the only numbers that we have to make sure that we have on our number line. Other than that, we're just going to fill in other things. So we want to fill in 2 and 0. So we'll go ahead and we'll put 0 right here. And 2 right about there. So for 2, for our f of x value, domain A, was that we excluded 2, but we got to include everything else. For g of x, for domain B, we include 0, and we include everything greater than 0. So that's that idea there with our domain. So our domain A intersect B has to be where x exists in both domains. So really what we're looking for in our image here for our number line is where do we have the colors blue and red and in what areas? So if we look at our graph here, we see that red covers everything except 2 and blue covers 0 and everything greater. So we have blue and red between the values of 0 and 2. And then we also have blue and red for everything greater than 2. So we can go ahead, portion those off. So we've got 0 to 2. Now we want to remember that 2 is not included. It cannot be included no matter what. So it has to have a parentheses. So we don't include it. But 0 is still included. So we can go ahead and we're going to put that square bracket still on 0. Then we have our other portion of our number line, everything greater than 2. But once again, we're not including 2. So 2 still gets a parentheses, and infinity always gets a parentheses. So in this case, the union of these two intervals is our domain. So the interval here are as for our domain 0 to 2, including 0, not including 2, union 2 to infinity, not including 2. This answer here, this is A intersect B. So that would be our answer. So the f plus g of x part wasn't too bad, especially since there wasn't a whole lot to do with combining them other than to actually just writing out the operation. As we said before, you could simplify. That would be the simplified answer that we see there, but you don't have to. It would be up to you. Our domain was the part that was just a little bit tougher because we wanted to kind of redraw those number lines to get that really good visual and see what does it mean to have A intersect B. Now, the good thing is from that slide in our lecture that we saw a while ago, the f plus g, f minus g, and f times g all have the same domain. The only time it changes is when you have f divided by g, and it's just that you also would have to exclude any number that would make your denominator 0. If you already excluded it, then you don't even have to think about it anymore. But if you hadn't excluded it yet, you would just exclude it then instead. So we'll see that when we get to that part. But the good news here is that we don't have to do any more work for the domain until part D now. The domain is going to be the same for A, B, and C. So we just need to find out those actual values and functions for A, B, and C. Domain is going to be the same. So we don't have to redo what we just did like every single time. So saying that, let's go ahead and move forward here. So for part B, we have f minus g. Remember, this insinuates f minus g of x, even though it's not actually written. So this is f of x minus g of x. We know what f of x is. We know what g of x is. This is going to be 1 divided by x minus 2 minus the square root of x. And yes, once again, you don't have to simplify it any further than that. If you do, it's going to look almost the exact same. It's going to be 1 minus the square root of x times x minus 2, all divided by x minus 2. So that's it simplified if you want to combine those two terms fully. But once again, WebAssign would accept the answer that's highlighted. There's no need to do relate any more than that. So you can definitely just leave it at that. Our domain, like we said, is the same. So domain for part B is 0 to 2, including 0, not including 2, and 2 to infinity, still not including 2. So there we have it. That's how we got for part B. So once you find out that A intersect B domain, it's really nice because you don't really have to deal with it anymore once you figure it out one time. So all right, now we have part C. We have F times G. Once again, this insinuates F times G of X, which is the same thing as F of X times G of X. So now we're multiplying the two functions. So we have 1 over X minus 2 times the square root of X. So we can actually combine these really easily. So we do want to do that. All that's going to happen is that that square root of X is going to go into the numerator. So we've got the square root of X divided by X minus 2. So that would be our answer for F of X times G of X. Once again, domain is the same. So our domain is once again 0 to 2 and 2 to infinity. Gets really nice once you don't have to compute domain again. But here we go, part D. So now we actually do have to take another look at domain. Not a lot is really going to change here, but we do have to kind of factor in that extra bit of information here with just knowing that G cannot be 0 because we can't divide by 0. So F divided by G insinuates F divided by G of X. This is the same thing as F of X divided by G of X. So F of X, as we know, is 1 over X minus 2. And G of X is the square root of X. We've got a really ugly looking function here, so we want to simplify this. We want to remember that division is the same thing as multiplying by the reciprocal. So we're going to keep that 1 over X minus 2 the same. But now instead of dividing by the square root of X, we're going to multiply that by the reciprocal of the square root of X. Now the reciprocal, remember, would be that if you had a fraction, you would just be flipping the numerator and denominator. Since we have the square root of X is the same thing as saying square root of X over 1. So the reciprocal is 1 over the square root of X. So we can multiply by the reciprocal again. That's what that looks like. And when we multiply these, we multiply our numerators straight across, so we still have 1. And we multiply our denominators straight across, which is going to give us the square root of X times X minus 2. And that is our function of F divided by G of X. So now comes that moment where we have to really reconsider domain. So the idea here now is that the domain is pretty much going to stay the same. The only thing we have to think about now is what value of X would make G of X equal 0, because we're going to exclude that number. So our domain was originally 0 to 2 and 2 to infinity. And we include 0, we don't include 2. We still can't include 2 because it would make our denominator 0, so that still checks out. But now we have the square root of X in the denominator as well. And whereas before we could take the square root of 0, the square root of 0 in this case would make our denominator 0. So the only thing that changes about our domain is that we just can no longer include 0. So our domain stays the same roughly. It's just that we now have a parentheses around 0 instead of a bracket, since we cannot include it anymore, since it would make our domain, or since it would make our denominator equal to 0. Woo. Just gonna put a little star around it. And can no longer include 0. So that's why we changed it from a square bracket to a parentheses. That's really the only change that we had to make in this case. Any change that would have been drastically any more different, I would recommend drawing another number line and getting your new answer. But in this case, all it took was changing, a bracket to a parentheses. So we didn't necessarily have to like redraw the entire number line. But if it was any more difficult, I would definitely recommend redrawing the number line. So, all right, that finishes up example 2. Let's go ahead and go back to our lecture. All right, that was example 2. So moving on, we're going to talk about the composition of functions. So this is our new operation. It's our new way of looking at our functions and combining two functions. So with the composition of functions, we say given two functions, f and g, the composite function looks like what we have here, f of G. So we have this circle in here, and that circle represents the word of. It almost looks like an O, so you can almost read it as fog. Sometimes I do that. So we have fog here, but it's also read as F of G. So this circle is a new operation, just like addition, subtraction, multiplication, division. It's just that it can only be used with actual functions. So we have our composite function F of G, also called just the composition of f and g, so you can see it be written a few different ways. And this is defined by saying f of g with the circle of x is equal to, and it's going to sound the exact same, f of g of x. So verbally, when I say it, it sounds the exact same, but it is written a little differently. But basically, if you ever see this circle and it's the composition, this is how it's written, where you have g of x inside the parentheses of f. So instead of just having f of x, you now have f of g of x. So it's kind of this double evaluation here for this type of operation that we have. So we're going to look at just a few different kind of visuals for this. First, we have this visual over here. This kind of represents that machine idea. So we talked about back when we learned about functions, we talked about the machine. We say that our function is kind of like a machine. We give it an input, it spits out an output. We also talked about that penny comparison. So you have those machines that you give it a penny and you crank it and it flattens out the penny and gives you like a little picture on it. This would be like you did it twice. Let's just say, you put a new picture on both sides of your penny, I guess. It doesn't work as great with composition, but something else does, which we're going to talk about that as well. But so with this visual here, we have g and f, so our two functions, g and f. We give the input to g, so we give x to g. G is a function, it spits out x squared plus 1, and you're going to take that result and put it into your function f. So giving x to g made g x squared plus 1. And then putting x squared plus 1 into the function of f, which in this case it does not have it written, but it's the square root of x. But now you have the square root of g of x. So since g of x is x squared plus 1, your final output would be the square root of x squared plus 1. So that's kind of that idea there. Then we have this picture over here. They look like beans, but I think they're supposed to represent domains of some kind. And they just look a little funny. But so what you have here is that you have that value of x, you give it to the function of g, and it gives you g of x. You take that value, that expression g of x, you give it to the function f, and it spits out f of g of x. So the composition function f of g, that f circled g, is just giving you this kind of double bump here. So the double evaluation without actually doing it two separate times. It's just one straight kind of way through there, one cycle. But we're actually going to go over to our notes really fast. We're going to do another little visual that I think works a little bit better than the ones we just saw. All right, so what we have here is we're going to use the idea of Russian nesting dolls or just nesting dolls in general. I actually do have a set of nesting dolls, but I did leave them in my office over the summer and I do not have them with me. So we're going to do a little visual instead. So the idea with these nesting dolls is that you have the one really small doll and it goes in the next doll, which opens up so it actually fits inside. And then you close it off and then you take that one and you put it in the next size doll and it, has a cap and you put the cap on, then you put it in the next doll and the same thing happens until you have the biggest one. So it's the same idea. It's nesting. We're nesting equations and functions within each other. So this idea that we have here with our functions is that same thing with the nesting dolls. So we would take, say, the smallest nesting doll, and we would go ahead and we would place it inside the next size doll. When we do that, that idea there of taking that variable x, putting it inside that next function that you have, in this case, g, when we do this, this whole thing, the combination, becomes g of x. We added x to the function of g, and this gave us g of x. So we have g of x in this case now because we have x inside of the function g. So what's going to happen now, and I'm going to put that in the same spot, what's going to happen now is that now that we have g of x, which is a pretty typical function that we would have, we're going to take this entire result, we're going to take that doll, and we're going to put it inside the next sized nesting doll. So we would take this whole result and put it inside this one. Might have been a little big, but it's fine. You get the idea. So we will put that next one inside the next nesting doll. So now in this case, we don't just have x in g, we have x in g, both of that in f. So, whoop, that was the wrong thing. So in this case, we had g of x, but now we have f of g of x. This is our result now. So we kind of saw this order here. We saw x went in g, and that result went in f. And that gave us our final result of f of g of x. So that is the idea behind our composition functions here. And they don't necessarily have to even be in this order. If we go ahead and we kind of reverse this order with what's f and what's g and whatnot, we see it come out quite a bit differently, although the process stays the same. So if we went ahead and we actually took this out and kind of relabeled everything, and if we just relabeled these, let's say the middle one is f and the big one is g, the same things would occur. It would just be labeled a little differently. So in this case, this would be f of x. And we would take f of x and put it, whoa, that was crazy. Take that back. We would take this result and place it inside our function g, and this would give us g of f of x. So in this case, we saw it was just the order that changed. So x went in f, and then that result went into g. So that was really the only thing that changed. You can change the order, which means that you would change the order of like how things got inputted, but the idea is still the same. It's this double evaluation. You're evaluating your first function at x, you're evaluating your second function at that function of x. So that's the idea. So let's go ahead and do an example so we actually kind of see how this has worked out. All right, so we're going to go ahead and do example 3. We're going to let f of x be equal to 2x. G of x is going to be the square root of x. And h of x is going to be x minus 3. So we're going to find the following functions. Part A, we're going to find f of g. Part B, we'll reverse that and do g of f. Part C, we're going to do h of h. So we're going to see kind of that double evaluation of itself. And then lastly, part D, we're going to have f of g of h. So let's go ahead and go over to our notes to work this out. All right, so here we are, example 3. We have f of x, g of x, and h of x, and we have each of our different compositions here. So for part A, we're going to start off with f of g. Now we're kind of saying that same thing. We don't have x written anywhere, but we want to remember that this f of g fog is the same thing as saying of x. So just want to keep that in mind. And this is also the same thing as saying f of g of x, like that. So we have f of g of x. Now that we have this, we can go ahead and replace our functions. So we're going to go from the outside in. You can go in either direction when it comes to these types of functions. You can go from the inside out, but either way, you should end up at the same answer no matter what. But so personally, I think that starting out, it is easier to go from the outside in than going from the inside out. There we go. So we can do it this way, but if it feels more natural, or if you've learned this before and it feels better to go from the inside out, you can definitely start that way as well. But all right, so going from the outside in means that we're going to start with f. F is the first function we're going to start with. And f of x is 2x. So when we do this problem, we're going to replace g of x with x in the original function. So bare basics, just instead of x, we're going to write g of x. So within our function, f of x is equal to 2x, but we're evaluating our function at g of x. So really this is going to look like 2 times g of x. Since we're now evaluating our function at g of x, not just x. So we have 2 times g of x. Now that we have this, we can simplify further because we know what g of x is. G of x is the square root of x. So in our final answer here, we would get 2 times g of x, which is the square root of x. So our composition f of g of x is 2 square root of x. All right, so that was part A. We're going to do the same thing for the rest of our functions here. So B, we have g of f. Remember, this insinuates g of f of x. So we can write this out. We can expand it a little bit more. This is going to be g of f of x. So it's a little bit opposite than what we just did here. But we're going to go about this the same way. So overall, we start with g because we're going from the outside in. So we start with g. We know that g of x is equal to the square root of x. So instead of writing x, because we're evaluating at f of x, we're going to replace f of x with x, or other way around. We're going to replace x with f of x. So when we write out this answer here, we start by writing out what g of x is supposed to be. It's supposed to be the square root of x, but we don't have x, we have f of x. So it's the square root of f of x. Now we know what f of x is. F of x is equal to 2x. So in our last step here of simplifying, we just replace f of x with its expression, 2x, and this gives us the square root of 2x. So we see here that the order does matter when it comes to your final answer, because we saw that f of g of x was 2 times the square root of x, but g of f of x was the square root of 2x. So we see it does change a little bit with the order in which we do it. So it's important to keep that in mind. All right, so our next one here is h of h. Now, as always, quick reminder, h of h, this insinuates h of hx, which is equal to h of, not 0, x. So this is the real function that we're looking at here. Since this is the real function that we're looking at, once again, we're still going from the outside in. We do have the same exact function in this case, so we're kind of just putting it inside of itself. So that's the idea here. So starting with the outside function, which is h, screen freaked out. But all right, so our outer function is h, so is our inner function. But starting with the outer one, we have h of x we know is equal to x minus 3. So h of x, which has an x minus 3, we're evaluating at h of x. So instead of x, we're going to write h of x instead in its place. So this will be equal to h, oh sorry, oh, wrong way. Yes, h of x minus 3. We're just gonna stick with that color actually. So within our function, we have h of x minus 3. So since we replaced the original x in h of x with another h of x, and once again, we know what h of x is. H of x is equal to x minus 3. We'll replace it again. So replacing it again gives us x minus 3 minus 3, which now we can simplify because this is x minus 3, which is equal to x minus 6. So that idea of evaluating a function of itself, so like the h of x, is that you're going to replace your h of x with its original function. And so with the original function that originally had x, remember x is just a placeholder for anything else. So we would replace that x with the h of x expression, like literally h of x, and then everything else stays the same. And then we once again replace h of x with what it's actually equal to. So in this case, we kind of saw that minus 3 happening twice in this case, which ended up giving us an x minus 6. So, all right, let's go ahead. We'll do our last one now. So our last one is f of g of h. This insinuates also of x. But writing this one out, we now have a 3-time kind of evaluation. So we have f of g of h of x. So this is what we're looking at now. So when it starts getting a little bit bigger, this is where it's better to try and kind of do that outward in instead of from the inside out, in my opinion. It's just a little bit easier that way. So here we go, starting with the outermost function. Outermost function in this case is f. So we know that f of x is equal to 2x. So when rewriting our function, we replace x with everything inside the parentheses. So we're going to replace x with g of h of x. So that's kind of what's happening here. So we're going to have 2 times g of h of x. So we saw that double, ooh, there we go. We saw that kind of double replacement there. So we now have 2 times whatever g of h of x is going to be. So now we want to go to the next one, the next function being g. So g in this case, g of x is the square root of x. But what we have here is that h of x is on the inside of g. So h of x is going to go in place of x. So what we have here still, so we still have that 2 on the outside. So we have now 2 times the square root of h of x. So this is what we're looking at now. We replace the x with h of x instead. And now we know what h of x is. It's x minus 3. So we're going to do that last replacement there. We're going to go down here. So we have 2 times the square root of x minus 3. And that would be that triple composition function there for this problem f of g of h. So we saw that kind of double evaluation happen twice instead of just once. So we got our final answer of 2 times the square root of x minus 3. So, all right, that finishes up example 3. Let's go ahead and head on back over to our lecture. All right, that was example 3. Let's go ahead and do example 4. This is our last example and the last thing for our lecture here. So last part, example 4. Given the function capital F of x is equal to 2x plus 1 to the power of 5, find the functions f and g such that f of g is equal to capital F. So in this case, we're kind of going a little bit backwards. We're saying this is the composition. What were the 2 functions that made this composition? So we're going a little bit backwards in this case, but let's go ahead and do it. So we'll go on over to our notes to work on this problem. All right, so here we are with problem 4. We have capital F of x is equal to 2x plus 1 to the power of 5. So we want to know what is f of x and what is g of x such that their composition is equal to capital F of x. So we have written here off to the side the f circle g or f of g of x is equal to f of g of x, where g of x is inside the function f to create capital F of x. So we're asking here what's going to be f of x and what's g of x to make this statement true. The funny thing about this problem is that there are actually quite a few correct answers. There are a lot of correct answers and 2 different functions that would create capital F of x. But there is one probably most basic, most kind of clear answer that we can pick. So that's the one that we're going to go ahead and go over first, and then we'll just kind of talk through some other ones. But all right, so the idea here with f of g of x is that we have an inner function and an outer function. The inner function is g of x, and the outer function is f of x, meaning that functions that you see that can be described as on the inside is going to be g of x, and anything that could be considered on the outside is going to be f of x. So if we look at our function even has parentheses, which makes this distinction quite a bit easier, because we see that 2x plus 1 is inside parentheses. Well, this power of 5 is on the outside. So if we know that f of g of x, which is capital F of x, we know that there's an inner function g of x and an outer function f of x. So we just have to determine which is going to be which. So in our case, 2x plus 1, we can really consider this an inner function. It's inside parentheses. It is inside the parentheses that has the power of 5 on it. So this is the inner function, and we know the inner function is g of x. So we can pretty safely say that g of x is 2x plus 1. Then on the opposite side here, we have something to the power of 5, the inner function to the power of 5. So if we're really looking at this, we have the inner function inside another type of function, which is that power. So if we're really thinking about this, if 2x plus 1 is g of x, we know that if it replaced x and f of x, x would have been taken over entirely by 2x plus 1. So the fact that that power of 5 is on the outside and we completely attributed the entire inner function to g of x, we can consider that the outer function was most likely x to the power of 5. So we can say x to the power of 5 is the outer function, which was f of x. So, and we can verify this if you would like. You can find f of g of x. So we would get, x is, or f of x is x to the power of 5. So in this case, we would have g of x to the power of 5, which g of x we know is 2x plus 1 all to the power of 5. So we do get that answer if we kind of check that answer there. So in this case, we do see 2x plus 1 is g of x, and x to the power of 5 would be f of x. We see that, when we take their composition, we get the correct answer of capital F of x. Another version that you could have had for this that is also correct would be something like your inner function being just 2 of 2x and having your outer function, or f of x, be x plus 1 to the power of 5, because you would replace that x with g of x being 2x. So that's another kind of correct answer. And like I said, there's many other correct answers to this problem, but what we just went over, what we just showed, was kind of the most basic one that we can think of. Whenever it comes to working backwards with composition functions, you really do want to look for what's in parentheses. Anything that's going to be in parentheses is most likely the inner function, and anything else is going to be the outer function. It made it that much easier by having parentheses in the first place, which is what they're most likely going to give you for problems like these, to make it as kind of obvious as possible on which should be which in this case. So, all right, that finished up example 4. Let's go ahead and go back to our lecture. All right, so we just finished up example 4, and that wraps up section 2.7. So in summary, in section 2.7, we covered adding, subtracting, multiplying, dividing functions, and we also covered composite functions. So we can now add composite functions into our arsenal of basic types of operations. So, all right, that was section 2.7, and I'll see you in the next one.